the speaker for the session. We are in the last day of the last day and the first session. This session will be taken care by Dr. Bibashan. So let us introduce Dr. Bibashan.
Good morning to one and all. I, on behalf of organizing committee, welcome you all on the final day of the program. We are extremely overwhelmed to get our first speaker of the day, Dr. Vivas Sen. He received the BTech degree in Computer Science and Engineering from NERIST, Arunachal Pradesh, India in 2002 and ME and PhD degrees in Computer Science and Engineering from IIEST, Shibpur, India in 2007 and 2015, respectively. He is currently working as an associate professor at the Department of Computer Science and Engineering, NIT Durgapur, West Bengal, India. Dr. Sen has several years of experience working in academia, government, and private sectors in research, teaching, consulting, project management, software design, and product engineering roles. His current research interests include hardware security, security systems for wireless sensing, hardware Trojan, quantum dot cellular automata, reversible logic, and fault-tolerant architectures for emerging nano devices. He has praiseworthy contribution in his research area, which includes more than 100 publications in highly standard journals and conferences. Dr. Sen was listed in Stanford University's world's top 2% scientists in 2021 for his extraordinary research work. Sir, it will be an honor for us to listen to you, and we'll also get to learn a lot from this session. With that, I want to add, we organizing committee are delighted to have you all here today. Over to you, sir.
Thank you all. This nice introduction. So, but I don't know how much I can expect this honor. But even though I would like to first thanks the organizer committee for giving the opportunity to share my idea to all of you. And regarding the this workshop, I think in this pandemic scenario, considering the pandemic scenario, this type of online interaction may be a little bit boosted our knowledge. Otherwise, this type of online earlier we never thought of. But in the pandemic, it teaches us that the show must go on, that we can't stop whatever may happen. So the research continues in this way. So first of all, I thanks again the head of the Department of the Information Technology, Tripura University, organizer Dr. Jayanta Pal for inviting me. And the bottom of my heart, I congratulate all the members who have joined this session. And please cooperate me whatever I am going to discuss. So today, am I audible and my slide is visible to you properly?
Yes, sir. Audible and visible to you.
Okay, okay. So today actually already this is the advanced topics. I think whatever he's told, the advanced topics in QC. So already I think I've studied a lot in quantum computing, but here we are studying a little bit not purely quantum computing, but here we are studying some field coupled nanotechnology which can mimic or you can say which can enable some quantum behavior, quantum phenomena. So it is you can say the applications of quantum phenomena in real life application. So after a lot of quantum concept, quantum information processing, now we are deriving some technology QC. If you earlier have joined in my previous lecture, I think it is a consecutive the second session of the workshop. In earlier, there is a first workshop where I have given the basic fundamentals of fault and reliability, all these things. Today, I will discuss how we can estimate the fault tolerance capability or reliability of the circuit with some advanced toolkit. So I am going to discuss some tools are required for this defects analysis, and these tools properly macro octave. One Italian researcher has first introduced this concept as DLK. You can search in the website, you can find out. So actually we have a high definition language for conventional VLSI. Conventional VLSI hardware description language like Verilog, like VHDL, this type of concepts are there in our conventional analysis of CMOS service circuit. What happened in case of VLSI, if we can utilize this in the QCA technology? So Macro Otavi first tried it and he eventually first developed this tool. That's why it's very similar to HDL name, but it's for QC. So little bit deviation we will follow, and I think those are from electronics background, they can easily understand. However, if you people have some query that you didn't understand, you can raise your voice so that we can proceed on this dimension. Okay. Now this is basics. So I think already we have studied earlier all the basic concepts. However, I would like to give some short basic on this thing that you at least you can understand these are the topics we have to discuss. Nothing more than this. Suppose what are QCA? If I consider the QCA, if actually in a island of this type of quantum wells are actually created. This type of quantum wells are created and electron is doped with some energy to the electron that when the energy of the kink energy of this particularly well is more than this, then only this comes out. So with this effect, a electron is doped here. However, electron can tunnel like in the within these wells. So these are the wells. Actually, these are nothing but like in this way. I'm telling. So these well, you are just seeing the virtually. If you give the top view, so this is the top view. Whatever we are simulating, actually, it is the top view. But I am telling, if you take a cross-sectional view, it's look like in this way. So you are just seeing this part only, that electron is present, so that's why black. Electron does not present, that's why you get the blank. So these things are here we introduced here. So Q date means are the particularly I am telling that where well electron is doped. The electron is comes out when the energy, the ground state energy more than the kink energy, whatever we can require to dope inside the circuit. So now it happens they can tunnel inside the QC. The problem is arises that since it is a why we call it a cellular automata. As we know earlier, Dell in our computer science there is a topic called finite automata. That is finite automata. That for any state behavior, maybe if I write to state like Q0, Q1, if I give one input X and for that output state changes. Like in this say Q0 may be cold state, Q1 may be hot state. Just like I'm writing. So if I X is electricity, if I provide the electricity, the machine becomes hot. And if I remove the electricity, machine becomes cold. So you can analyze this is nothing but an iron. So I am analyzing the machine with some logical diagram. So same thing, if a state for a particular input changes, so we call that definitely not more than two states are possible. I am not telling, I am telling definite in one state. For a particular input, when the state changes, so particularly one dimensional, then we call it is, generally we call it our main finite automata. But here is that a state only affected by its input, not other than this. But in case if a state behavior not only input for the other state whatever present, they also introduce in presence of these two cells this condition, then Q go to the Q state. Not only input depends on the other state, then this concept is called cellular automata. Just like a cellular architecture, that means the behavior of the state does not depends upon on the input, depends on the neighbors other states also which can influence him and go to the particular state. Same thing in QC also, you will find that whenever a state of the circuit changes, it does not only changes, it's in particularly see this cell. This cell has the influence of this one, this one, this one. Neighbor cell will give a you can resultant impact on that particular cell, and then accordingly its state will be changed or state will be defined. So each stage does not depends only is only single input, or it's a neighbor particular whatever input you are giving from outsource. It depends upon the neighbor cells influence also. That's why it's also cellular automata principle it is followed, and inside it, since the quantum phenomena is there, so we call it a QCA. So that is the one simple background we can analyze inside this QCA. Now what happened that is a field coupling. So actually we are creating a field. Just after this slide we will show you one quantum phenomena behavior in our lecture, where you will find a magnetic field like electric field is created by a clocking circuit, and that will induce the cell in particular polarization, and that polarization will impact the other cell, and consecutively the impact will go. That's why it is very very important the cell's position is very very important for getting the actual polarization of the output. You can notice it here. If you can place the cell in such a way, it becomes, and diagonally due to the influence of the cell, it becomes the negative. If it is 0, it becomes 1. If it is 1, it becomes 0. That means just reverse happen in these cases. This is diagonally. That means why? Because if you analyze the diagonal cell, if electrons are there, automatically it will repulse the electron here, the electrons will go there. So it will happen like in this way. Because of that, because repulsion of the coulombic repulsion of the cells, it will go to the diagonal. So that's why always you will get the reverse of the polarization here. So here we will find the negative polarization, opposite polarization. Same thing, influence of these two will be opposite polarization. So these are the possible inverter connection. That means if you provide here 1, you will get 0, and vice versa, reverse you will get. This is the basic prominent gate in our QCA because this is a majority voter. You know, if I apply here A, B, C, whatever P, Q are written, you can induce all these thing output. The F is the function defined by this one. Now, if you notice it, if I fix any one input is 0, it becomes as a AND gate. If I fix any input as a 1, it becomes OR gate. Mostly this cell is the logic or driver cell. We can say this is the driver cell. The basic problem of the driver cell is that each stage is defined by the consecutive influence of these three cells. So accordingly, this logically propagated. Here, the initial condition when the electrons are in ground state, the polarization defined by the underlying clocking circuit will the main driver or is the power source provided for the circuit. So these are the different fundamentals as I described here used in the QC circuit analyzation. You will find one more thing there. Orientation also differ. This also a great impact in the circuit. It is found in the QC that if the different orientations are laid together, they will not influence each other. That means just like in this way, electron will pass. That means if Q equal to 0, 0 will automatically pass here. However, P may be 1, 1 will pass here. So that way, a wire crossing can be built out. So you understand wire crossing is the possibility here. However, wire crossing can be multi-layer also. This multi-layer concept is very, very critical in nanotechnology. So that's why we are not highlighting this course or these features in our lecture, because generally whatever we have found the literature, this is only in theoretical level. It is never realized in practically. However, this also realized, but not in room temperature. The viability is more than this due to the complexity. So we are focusing on the coplanar structure only. Now in behavior, you notice it, the different color you are noticing in the circuit. The different color indicates the phase of the clocks. Initial cases, this is we can say 0 phase. After that 1, and then find 2, and finally you will find 3. Different color we have shown. The green color 0, 1, cyan color 1, and this magenta and cyan color 1 and 2, and this the whitish color is the 3. It means that when ground state polarization starts switching from ground state to some definite polarization is start. Maybe initial cases, one in ideal stage, a QC polarized is undefined. Undefined, that means it can be this can this electron continuous fluctuating, so are not getting any stable configuration from this one. The electrons are continuous tunneling in the ground state. To make it a fixed polarization, we'll start providing by the clocking circuit to polarize it, whatever input I would like to give. And that's why you find that after some time, it's come as a fixed polarization. So from the ground to fixed polarization, we call it a switch state. That we have explained here a little bit. The ground to switch when you get go, then we can say this is the switch state. That means now you are in ground. That means no definite polarizations are there, and then it is attained some fixed polarization. So up to that, it is some fixed polarization achieved. When fixed are achieved, then it try induce to other. After that, it will influence the next neighbor cell. So now it starts polarizing neighbor cell. So neighbor cell situation is like in this way. Your current cell, if I have a two cell A and B, so initially A was there. When A achieved this stage, then B stage is here because B now polarized. Like in this way, the signals are transition from one cell to another cell and one cell to another. In this way, electrons positions already define the propagations of the signal. So now with the transition of the signal, now this is the stage when it polarizes its neighbor cell completely, then it depolarizing started. So automatically its polarization diminishes. Now it will polarize its neighbor cell. So like in this way, you will find whatever I have said here, this is started, the signals is propagated like in this way by the influence of clocking. Here, no flow of electricity. No flow of electricity, only the repulsion, or you can say attraction, which defines the position, which defines the position of the electron, position of the electron will take the signal propagation and signal transition cost. So these are the basic, actually we given lectures in our previous version of this quantum computing. So my request to all of you, any question in this part, whatever I've discussed from your side, any question, so you can ask me. These are the some references in the website I have given for getting the details idea from these slides. Okay, any question? Then I will proceed. I thought that you understood it well. Since this type of faculty development program is not for only that I will deliver the lecture and what will be the carry out, or you can say the outcome of this workshop that you will take away from this lecture. So here one of the takeaway you can say that these are the different issues you can address in your research domain, and anyone can start a new research in this domain because this is still under in research domain, cost efficient, reliable, QC. So what happened there? The underlying structure, that means main issue of the viability of the nanostructure or its sustainability depends upon is main underlying unreliability, because huge reliability and unreliability happen due to its high and low power. These are main nanoscale devices are acceptable and highly demanding technology. But the problem is that the bottom up self assembly technology and to make it regular structure or their proper interconnection is very, very challenging. That anyone can start in this way. So to regular structure interconnect, you can follow different regular clock QCA circuit, how it can be done. We'll analyze in the later of the circuit also. You will find some configurable QCA part that is also very important. We'll discuss little bit, however, but our main concern of the lecture is that testable QCA, how we can do with the HDLQ toolkit. If you notice that the system level or the processor, I am telling that whatever generally you see in your motherboard or system board. But if you go little bit deeper and deeper, finally, if you reach at the physical level, that means at the you can say atomic level, you will find that the performance of these two issues are very critical. That means during the fabrication, it may happen that as I expected, the three cell layer can be this way, but maybe one cell not properly doped, or maybe one cell not in proper position. So lot of issues have discussed by this Bahar scientist in the in Iris Bahar et al. He has given some overlook on this different silicon nanotechnologies and beyond architecture in this journal. So what I would like to impose it during the fabrication. So this is our expecting normal behavior, that the electron should position, the two three QC cells should be there like in this way, and one more. So actually a five layer 5 QCA cell we are targeting to organize in this way, but it may happen that in nanofabrication one cell not properly doped, so the structure become like in this way. You don't know it is developed or not, then you have to test it. So this is called cell emission, and it may happen that it is little bit placed from my desired location to upper, maybe in horizontal movement. So these are the possible two cases. Maybe vertically it is shifted, maybe horizontally shifted from its original position. Why I am telling original position? Because if the QC cells are not positioned properly, the actual functionality of the circuit cannot be evolved or it cannot be generated. So that's why its position is very important, because the combined effect of the all the QC cells will couple together to generate all this. So that is the very important thing. So generally in question asks in different exam also, that is it possible that cell emission and cell diffusion can be detected in QC? Because conventional technology does not support to test all this. So we will adapt. It is possible to detect whether cell is properly by providing the particular input, particular output will get. Sometimes it may found that for particular input it is running, but I don't know in all cases this logic gate will be applicable or not, because it is a reduced of induced of area in a long direction. Actually the problem is that if it is placed from original position, because every QCS cell has some, you can say, cell of influence area. That means if any cell coming in this domain, the cell induced of area, we can say induced area, any cells present in this area, it have some impact of the circuit. So every cell have some induced area, so you will get continuous overlapping of induced area between them, so it's a great influences there. That's why you will find that these are two situation is very important. As well as it happened that in fabrication, during the fabrication of the cells, you may find it that already extra cells are deposited. Then again this situation will arises, or you may found the cell is rotated from its position. So these are the possible or defect is coming. In case of our conventional, you find that our circuit, due to the transistor circuit, generally whatever transistor circuit we follow, grounding issues, sometime these or this time may be shorted. So what happen if shorted? If you provide 0 here, it may happen that you provide 1 here, but again 0 will be propagated here due to the shorted of this one. Generally we call it the stockade fault. You can give 0, but you never get 0 1 due to the stockade fault with other circuit or something else, or grounding. It may happen. Maybe individual grounding also it arises. So we'll find that stockade fault, stockade 0, or stockade 1. These are the common fault generally found in the conventional CMOS. But I don't know this type of concept will be available here or not. So this is a big critical issue. Generally, we can't expect it. So what should I do to analyze properly? We will analyze little bit of the clock. As I have told earlier, the clock is the main source of driver. You can say it is a main source of power, as well as you can say synchronizer. Power as well as synchronizer. So very important thing during the development of the QCA, all of you must think about these things, that it should be properly organized. Now what you find there, actually you will find that the clock zone, whatever you are getting the above level, it is just look like in this way, it is induced by this cell. That means this is the metal line which is buried under the QCA cell. If this is the QCA molecules, underline the QCA molecules, these lines are buried. And above that, actually it is influences some area in the cell. The crossing can be done with the metal wire like in this way so that they can't induce each other. That is for clocking circuit I am telling. So how electric field are generated and that will influence the particular cell. So automatically a cell be above it will induced by the electric field generated by this clock zone. Okay, so it is present beside below the circuit. If you notice it properly, if it is a QC cell, like you are getting the clock layer wire. I am telling this part actually present below it. Now you see, if our my QC cells are organized, you see that all the QC clock zones are below the circuits are embedded. So you will find finally that behavior, that is three layer, one clock layer, QC layer, and this is the protection metal conductor. That means you will find a three layer in the QC layer. So this is the fundamental QC layer, a metal conductor which will conduct the behavior of the QC or input output, whereas the induced power source will be given the clocking circuit. So these are actually sandwich in different layer and together a QC cells are like in this way form. So it is a very complex structure we follow. Now different clocking scheme are found in our literature. You can follow. Already we have also followed some clocking architecture. Someone have also different clocking architecture. Every clocking structure has its pros and cons. So as per your demand, you can develop the necessary clocking circuit. So now we are approaching our main topics, that is called HDL2, hardware description language for QC. So what is the HDL model which describes the QC devices and facilitated the evolution of the design? Utilize Verilog QC delivery library. Verilog counterparts of QC consist of Verilog HDL library. Now I am coming to the point is that why actually this become essential. First of all, already I told that the behavior of the QC circuit is not same as the quantum circuit, because the cell's position is the main reason behind it, because they have some induced area. So since it will be disturbed, so their behavior will be the same, not like a target fall. But here we are trying to utilize our conventional technology in our domain. So what should we do? First, we will go for the Verilog counter of the QCA. That means in QCA, we know we have a majority voter, we have a inverter, we have a fan out, we have a crosshair. All this architecture with some fault injection capability, that I will inject the fault and I will check the behavior. Why I will inject the fault? If a circuit I have injected the fault and I am getting the expected behavior, is some fault occur or not. Actually, I can guess it. Yes, there is a fault, or I can say is there is no fault. Now, if I did not get the, if I even after injection of the fault also I get the correct, so I can say that even though circuit the fault is occurred, it can tolerate. So actually by this toolkit I can analyze the fault tolerance capability also. How much fault even the circuit occurred the fault, but it can tolerate. So that is the main issue. I already told the famous scientist Macro Ottabi already with his team has developed this toolkit, and first we have got the idea. So credit goes to this person that lot of things which earlier do by manually, he can solve by this toolkit easily. It reduces the complexity in design and solution times, that are very important. Flexibility in timing and clocking analysis also, and the model of testing and validation of the QC system, and above all, the fault injection capability of the HDLQ system help us to do it more better way. Now let's see what is HDLQ modeling. If we notice it that properly, these are the possible QCS circuit available in our literature also. So this is the one circuit we call the RQCM. We have developed, and the paper is published in SCM JETC journal. You can search it, you will find it. So from that paper, I have given some extract. What happened that if you notice it, what is D0 I have mentioned, What is D1, D2 I have mentioned. These are to identify the data in that particular clocking zone. So you can understand the cell in particular clocking zone I have mentioned D0. That means all these cells are under in clocking influence of clock 0 that I have already shown underlying clocking zones showing the 0. And all the D1, whatever you find the D1, that is underlying clocking in clock zone 1. So like in different clock zones I have shown. Apart from that, sorry, apart from that, you will find that here I have just logical layout of the clock zones I have shown. Now, if I implement the HDLCO, how does it look? Let's check one HDLCO circuit first, then I'll come to here. Suppose this is a one CFA circuit. Here, in earlier circuit, I have shown with the clocks. Now I am showing the actual logic unit, which is the main thing. If it is visible, you will find it that here I have mentioned wire across one, WC1. There is a wire across. So this is I have written here wire across. Here directly there is a, I think, cross are there, then L shape wire are there. That means it L shape or not L shape. I'm saying that input is going here up to here. You that input are driven for here. That means one input is coming here, one input is coming here, one input goes below, one goes side. So it is just like a fan out. The signal fan out is there. That's why I have given this is a fan out. FO1 fan out. You will get fan out here also. That's why I'm writing FO2. Now you will find that there is a majority voter. So I have given its name MAG1. You will find that it is just like a wire, but it is L shape. L shape has a significance because this cell may be deleted or maybe omitted or maybe not fabricated properly. So if this cell is not fabricated properly, if this cell does, so it will become inversion. So it is a strong effect. So that's why I have given L shape wire also. So all this particular module I have here encompasses with different circuit. If you notice it, you will find that all these things I have given. So this is the output. Finally, this is the output. Before the output, you see there is the inversion logic. So you will find there is the inversion logic. Okay, then you will find there is a logic called LM. That means some after coming this it will pass here. This is a pass here in this way. So all these things we have developed. Is it clear how I have drawn this circuit from here? Because after making this circuit, only I can write the HDLQ code. Verilog equivalent HDLQ code we can write from this module. So I am asking that from anyone clear these things? Anyone from your side? Is it clear? Can I proceed that I'll understand this part is clear? Are there any student?
Yes, sir, you can proceed.
Okay. So there is no question as far I have understood. So you find that there is also inversion logic, and after the inversion, you will find that the circuit goes. So inversion, and they are getting that the circuit is coming here. Here also you will find that after this logic, you will find these are the all inversion logic, and I have mentioned all these here. Very important critical. So what I have found, one is wire crossing, one is L-shaped wire, one is majority voter, one is inverter. These are very important. Sometimes some output of the circuit is driven to the input of the circuit. So that also I have to propagate here. Like in this way, you will find that I have developed different the another circuit like TQCA. If you check, I have given different circuit. Why it is colored differently, I will explain later. For time being, you just check it that I have shown all this module here one by one. Now my observation is that after developing what I have to do, after developing Now you can go for the parity check techniques, reduce the complexity of the testing. The parity preserving logic gate, parity of output matches with their input, and show detection of fault. For the for all circuit I can't do, but for the circuit we can necessarily input. So before that coming, I am now writing the code for the actual circuit. Suppose this is the code, actually very low code we have mentioned. Already we have mentioned some very low code. If you notice it, notice see, I have given all the module, the fan out module. What is fan out module? In the fan out module, you check that some inputs are there, some input will be there, then some output will be there. So this is the input, this is the output. Two output is possible in case of fan out, and there can be a fault. So if you notice it in input circuit, now here you will find that input in and that fault also I can give you the input when I do the fault injection. Output will be output 1 and output 2, because it happens there whenever any circuit, if you give some input in the fan out circuit, two outputs come out, always fan out. That means I am telling that it can be splitted. So this is the input, now this is the output. So this is the input, this is the output 1, output 2. So that's why we mentioned here, in these cases you will find that in the fan out I have given one is input. What are the inputs I have given? Sometimes fault I can inject, and these are normal input whatever I have injected. And output is there, output 1, output 2, which of the fan out come out. Now what happened, I found that initial case I have assigned out equal to in. That means fan out, whatever the input I'll give, this will come out. Now in second cases, output 2, what happened that generally what output assign output, what I am assigning, if there is a fault. So this is the conditional statement. You notice it, if there is a fault true, then effect of the fault will be there. Otherwise, without there is no fault, effect will be there. That means there is no fault, and this is the fault. So if this condition true, outcome will be this one. If this condition is false, outcome will be this one. So this is actually happen in these cases. Now we can go for this one circuit. Just 1 minute. If you notice it properly, you will go for this circuit. What happened that in assign out, if there is a fault, what if there is a fault? If there is a fault, then the input will go. Otherwise, normal will go. Generally, it happen. So that depends how you would analyze the circuit behavior. I am telling that if fan out is normal, if I provide one, one will go this side, one will go this side. As per QC cell logic, suppose due to the cell misplaced something or anything, I consider this one will go there and zero will go there. So this is a fault. In vice versa also I can do. If this situation happen, one may go there, other will be faulty. If there is any issue in the fan out. So this is the presumption I have considered here. That means if in faulty behavior, after fault if I introduce, so one of the two fan out, and generally fan out should be same. So here will be fan out will be complementary or inverted. I am telling fan out will be inverted. Okay. So that's why, like in this fan out, I have given one example. Now in case of L-shape wire also same thing. What happened in L-shape wire? We know in L-shape wire the cells are placed like in this way. If you remove this cell, then automatically cells are placed diagonally, because there is no more cells. It will induce inverted way. It is in inverted feature. So that's why in our logic circuit you will find that in L-shape wire, generally first in L-shape wire what input will be there? output will be there and fault will be there. So if fault equal to 1, then output is inverted. Is the comment I have given. That's why I given double line. So that's why here input equal to input and fault, output will to output, because very well you have to understand which is the port you are using. Now assign out. If there is a fault, it will be inverted. If there is no fault, it will be normal. So like in this way, L shape I have defined. So different all the different shape where the behavior you analyze like in this way. So actually in QCA, due to the cell misplaced or cell omission, what are the features are there that we have captured here. Initially for crossing where, in crossing also, if output 1, if there is a fault 0, that means fault 0 in crossing is there. So each inversion will check. Again inversion will the what is the effect of the fault 1. If fault 1 also negative, then only invert will be there, otherwise inversion 1 will go. That means after the fault, how the output of the circuit will be analyzed. So that's we have defined here. So like in this way, for the entire circuit, we develop different code here. Now if you notice it, sorry, if you notice it, maybe in majority voter, let's check the majority voter. The very important thing, the majority voter, the behavior what we captured for that manually, we have analyzed all these features earlier, that if some cell is missing, what will happen. You check, there will be a sign. Now input different where I will define, because majority voter, the output will go in multiple direction, output will come. If I apply some fault here, if there is fault, then what will be the consequence? If there is no fault, what is the outcome? Same thing, if there is a fault, what are the this and what are the consequences? So actually directly I have considered different faults and is considered this behavior is completely as per the QCA. I am writing the code like in the very log way, but the behavior scenario we have captured. So this is the very simplest way we are analyzing it. Instead of the multiple times, you can do. Now if I say this code, now in this entire code we have developed the as per your circuit behavior or logic unit, you will do all these things. After that you will find it when I am simulating the circuit. I have giving the defined condition. This is the initial condition. When the all faults are 0, then automatically if all these are the fault injection I have not done. When after that you get the normal behave the circuit, when you start injecting the fault, suppose the fault here injected here, no, so here up to this nothing we have injected. Now fault injection start here. Normally if you give some input for fan out or fan input 0 or 1 considerably, whenever you give the input, because this is the different combination B C you have considered, so accordingly the output behavior you will pass it, and now you start run one by one injecting. But by manually you set this equal to 1, or manually you set this equal to 1, or manually you set this equal to 1. Once you set this one, if you run the entire code, automatically this fault will be injected, and particularly module where fan out 6 will be there, the fan out 6 I am injecting module. Maybe you are fixing it is a 1, so particularly you are injecting the fault there. So in by default initial cases I have not injected any fault. So for different combinations of A, B, C, here initially A equal to 0, so now B 0, C 1. So after A 0, B 0, C 0, that means my combination input A0 B0, now you are giving input 1. So that's why A is fixed, now B and C is combination like in this way. So that's why I have given after 10 second or 10 nanosecond microsecond, whatever may be unit of time, you will get this equal to 0 and 1. Got it? Now 1 0. That means actually you are going 0 1 0. This, now you see I have configured here B equal to 1, C equal to 0. Already A I have not changed, so A is still 0. And now finally C equal to 1. That means B I have not changed. So you will find here 0 1 1. So like in this way, in presence of A, in presence of B. So these are nothing but I have implemented the truth table. Understood? So this is my truth table input for real time I will give. And these are the circuit where I have given the A or B as a input and necessary all the module, whatever output and input is coming, I just configure this circuit. So this is the entire circuit I have written in our Verilog code. Which circuit I am telling? I am telling for this circuit. This circuit I have entirely written for all this. Where is the fan out? When fan out 3 will come, where it will go for which circuit. Now suppose fan out 1 will go WC1 as well as fan out go to fan out 6. So let's see fan out 1. Fan is coming from where? The out for fan out 1. So this goes to W cross 6 1. So see, it is the input in case of crosswire. Crosswire first one is the input. So input is coming for fan out, and it also the input for the FO6. Where FO6 is there, you should find out FO6 is the FO6. Now you see the output of the fan out one. The output of the fan out one. What is the output of the fan out one? These and these. So this is this input. So these now input to particularly the circuit as well as these input out to, sorry, these are two input, one for this circuit and one for fan out 6. So what is the fan out 6? I think this one. You notice properly, you check it, notice it. That means the output of this fan out 1, it is go to the wire across 1 1. So I am writing output 1 fan out 1, and this go output 2 for fan out 1 output 2. So it is output 1 output 2. You notice it that output 1 goes to the wire cross and output 2 goes to FO6. So like in this way, the where the circuit which output we are considering here to go in which way, entire things we have configured here with each of the modules. Here each of the module. You notice WC1 as the input B. So let's see WC1. WC1. See there is the input B. WC is two input. One is input there and one is there. So both the input I have considered here. Sorry, considered here. So actually I would like to mention that the entire circuit I have now written in this Verilog code using that particular module. Now you start simulating the circuit. Then when you first simulate, your behavior looks like in this way. If you first simulate, you will come. I have not Verilog. This is the variable part. See, whatever you will get in this first part, this is the first part I am telling. This is for normal behavior you are considering. Okay, this is only normal behavior. But what happened in these cases? In these cases, after injecting the fault, if there is no fault, then this will be same as this. But if there is matching, that means parity mismatch. Sometimes you can check the bit pattern also. Generally, we follow first the bit pattern. Let's see how does it look. That's I have analyzed here. This is my input vector. For whom? For this circuit for input vector. From the input, what is the output? That is the my expected vector of the output, the as per the circuit. Now I have injected one fault. Injected fault means sometimes this is for CFA circuit. I know. Okay, let's go for the CFA circuit. Maybe if I input this circuit, so I can do one fault here. Where is the fault? I can induce fault here. In WC, there is the input C and there is the output of this circuit. So anyone you inject as a fault, suppose generally I am say the WC and output I have made in fault. So if you make it fault, that means I have to go on that variable and make it fix as a 1. Instead of 0, you fix it 1. In by default, I have given 0, that means there is no fault. When any of the fault input or fault output, you will fix 1, automatically the behavior of the circuit will change as per our requirement. Requirement, I am telling that as per the behavior of the circuit. So here I found that once I have made one fault injected, that's why if you notice that I have given here fault injected, that means this is the normal behavior of the circuit. And what I mentioned that if you fix one or this one, any one, then if you fix two, that means the multiple fault you are injecting. If you are fault at a time only one, single fault you analyze it. So both are capturing here, and automatically the changing the variable, you will get the different scenario. Maybe on examples I have given here, that means this output of this output, both the output from the fan out. So one output for this circuit will go to the FO6 that I have given, it goes to FO6, and one output go WC1. You found that this for corresponding it goes to WC1, so it is go to here. So for that purpose, we have shown these are the two. Now, if I inject fault, that means either this for circuit, that means I am injecting fault in this module. So you are injecting a fault in this module, that means I will make it 1. So where is this variable 1? Fault FO1. So fault FO1, that means here. If you fix it 1, actually you are injecting fault here. Now you will analyze the entire circuit you run, then you will get what happened of this fault in the circuit properly. So like in this way, this entire circuit will be simulated and you will find that we people are doing this match. Is parity match? That means if there is a some parity of the input output is matching, this okay. But generally we check with the instead of parity, we checking the input output factors. How? I am telling, maybe my desired vector is here A4. A4 means I am telling 100 binary format, that I mentioned here A4. A0 means 000 binary, I mentioned is a A0. So what was the expected goal? A4. Is it coming here? Is it not coming here? Is it coming here? No. Actually, A4 is not coming, it is A7. That means there is a faulty behavior, not expected. But you see, some cases, even for the fault also, the output not changes. Fault in other logic maybe, not in LS1 or something else. So like in this way, after getting for all the combination, for all input, after injecting the fault, you will get some circuit. You will find that somewhere the variable input pattern is remains same. If you visit some circuit F4, it is coming here, 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 expected. This should be there. So when you have fault injected, amount 26, amount to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I think near about the 50 or something you're coming, or you have to check some more circuit there. Among 26, among 26, 1, 2, 3, 4, oh sorry, 3, 4. Here 4 is coming, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12. So 12 among 26 or 12, 13, 13. Huh? So near about this amount of percentage is coming correctly. This is around 50. Okay. Here 13. here from 14 to 26 is F. Now you will find for A1 output should be S6, and S is coming here, 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 here. So fault tolerance capability of the circuit here more merely comparing the others to condition. So like in this way, we have estimated and we finally take the average is what is the fault tolerance capability. So circuit has some resistance that after induction of the fault also, it is very, very less. Now, where is the very poor fault tolerance capability? You will find very poor in this cases. That means for input this combination, you are getting very poor performance. That means fault tolerance capability very less even for each of the combination of the different fault I have injected. These are different fault. That means whenever you fix any input, any of the fault input one, so one pattern is generated. Again, you do another pattern is generated. So like in this way, you can check for individual all these assessments. So that we have done here. So that is the fault model, and correspondingly using this concept you can test the entire circuit sufficient correctly. Another modern approach that we have not so discussed nowadays, QCA Pro, there is a QCA Pro and the QCAE. Two software tools are there for analyzing the energy or use the band energy. That means if you notice it, particularly majority voter have some huge power consumption. I know it is a low power, but even though there is some power consumption in the micro electron volt or milli-electron volt, here you will find that most of the time the tilt, the circuit in the normal wire across normal, that means wire, there is a very less power consumption. But whenever a cell is influenced by multiple cells, you will get the corresponding output as a high error rate of the power dissipation. So this is the one another part to analyze the fault, analyze the reliability or the performance of the circuit efficiency. When multiple cells are introduced each other, you will get that their fault, that we analyze covered is very less. So this is the one dimension analysis you can do for this part. So sequences of execution, I am telling that some toolkits are there. Icarus is a website available. So you can install it. Icarus available for a Windows system. If not done, you go for these software sources. You can install it. And in the environment variable, you give the variable path where you actually your bin files is there after installation. Now in the notepad with V extension folder, you can write the entire code. That means command probe, administrative type C, and verilog bin command. So actually running that main V function actually where I have written the entire code. So this is the code of the circuit where I have written. Are you getting my point? So you write the entire circuit here. That is there I have created already. So you can rename the circuit also. Now analyze the circuit for the parity, and if there is a mismatch, it will highlight. Not require parity, you can direct Verilog run the circuit automatically. You directly check it. Parity is the famous technique where for parity based circuit you can utilize also. So that's the different steps I have mentioned here. Here also I have given how to run this code. This command prompt also you can go for the run as administrator. Then the step C, the bag where there is no error after the compiling or are doing the circuit, that you see the command I verilog. And now if you write for BBB for parity, if you analyze the circuit, there is the result you will get. If parity there is no mismatch, so I think there will be no error. You can check the parity in the circuit. So that's up to this HDLCO code and HDLCO running feasibility we have analysis. Okay, so thus in this way you can analyze the behavior of the QC. I think now from here also one thing you can do, that how this code we have done from different pattern you can analyze, but some circuit is that parity. Here is a very simple way. That means I am not doing any parity. I am checking the input pattern which was not coming as expected. For particular input combination, I have found this fault coverage. Then how much fault it can tolerate. Other way, if there is a error properly propagating the circuit or not, that you can analyze use some like in this way. That means parity mismatch circuit. So since our CFA circuit, particularly this was that is conservative in nature, that means in CFA circuit, if you notice the CFA circuit already published in this journal, here you will find there is a parity input and output. And if the parity mismatch, I can say the circuit faulty, not tolerate that error for particular module. Okay, so that's up to the lectures from my side. So I would like to ask any question from your side. Any question from you?
Yeah, any question from the participant, please?
If you understood, that's good. If you don't understand, no problem. You go through those papers, then whatever discussions I have given, if you analyze it, because no QC's papers, whenever going to establish without this type of simulation, the standard benchmarks or standard simulation, if you do research contribution does not impact at all. So if you do it, I think you will get some better output, sir. Okay, I think there's a 90 students, so I think some students maybe little bit ask some question, even though I expected. I don't know whether you have it or not. Okay, so that's up to from my side.
If, sir, this software can be installed in Windows
Yeah,
or Linux.
I Icarus is a Windows and both versions are there for very long. So you can Windows versions are there, you can utilize it also available. Is an open
Sir,
source. Is an open source.
okay. Sir, is there any hardware available to that is analysis in the hardware platform, this circuit, design circuit?
No, actually, still the viability of the Q says room temperature is available, so you will not get open market. All these devices is under research, so you can simulate the behavior of the circuit in QC designer, and after implementing the circuit functionality, then from the circuit you just manually, or you can say implement the logic schematic diagram and then do. But whatever you will do, the behavior will be already mimicked by the simulator. So you can use QC designer for the actual circuit, what are you expecting for the main circuit, and then HDLQ for analyze the behavior of the faulty behavior of the circuit. As such, no hardware in the market available for the circuit. It is still in research level.
Okay, thank you, sir. And you have shown that fault tolerance measurement. You have shown it.
Yes,
So,
yes.
any type of there is any limitation to study the circuit that this output parameter only we can simulate, or any suppose if I want to design that circuit in the communication field. So what will be the nature of the output if we are using the quantum information? That type of application, is it possible?
Yeah, in our particularly in nano communication, if the field is in still research, nano communication, so many communication devices are there, filter circuit, or you can say noise filtering circuit, how you can develop the QCA. You can study all this at all also. In nano
Oh,
communication crossbars, all these things you can develop by QC circuit. So those QC circuit you can develop. And then
okay,
also, if some errors happen, whatever in your case is noise, how we can do all these things, that is the very important point.
okay. Thank you, sir. Can you get this your email, sir?
Yeah, my
Email ID.
emails, no issue. I'm in chat box is writing. So
Sir, coordinator, I am just requesting coordinator if you just give that email address in our WhatsApp group, so it will be
Yeah,
helpful.
actually, ma'am, I have shared the timing, that is the schedule, in the WhatsApp group, and there I have also mentioned the email ID of all the speakers.
Okay, okay, okay. Thank, okay,
Okay,
thank.
so yesterday itself, I have posted the updated schedule, and there I have mentioned all the the email IDs of all the speakers. So you can get the email ID whoever you want from that single file only.
Okay, thank you. Thank you, sir. Thank you, sir.
Thank you, ma'am.
Sir, I
Great.
have a one question.
Yes, Mosam. Yes,
Yes,
Mosam.
sir. Yes, sir. Sir, yes, and it is very nice talk actually. Sir, I want to know one thing, sir. What about the QC circuit that is follow some particular standard fault models which we are using in classical circuit, or
In
their own specific, that means QC circuit, their own specific fault models are there so that we
yeah,
can, yes, sir.
actually, what happened initially before the invention of the HDLQ, we do manually. That means replace the cell and then get the output and behavior analyzed. Accordingly, it is done. So tremendous research was done for cell omission, cell use. So its fault behavior is completely so not with classical. So there is a first distinction that in classical QC, CMOS circuit, you will find stacked fault, bridge fault. This type of fault arises in classical, but this type of fault not arises in the QCA. So the behavior, whatever I have explained by the HDLQ, this is purely the fault model for the QCS. Okay, so
Okay,
this
sir.
is
Okay,
for
sir. Okay,
QC
sir. I
circuit.
got it, sir.
Yeah. So that model
Okay,
you have
thank
to
you.
develop first. Yeah.
Yes, sir. Yes, sir. Thank you, sir. Thank you very much.
Any other query? Okay, I think no further questions. So I would like to get the
Yeah,
permission from the
yes, sir. I
organizer.
think there is no further queries. So
Okay.
I'd like to thank you very much, sir, for your kind session, and you have always been kind enough to deliver your expertise in all our previous as well as this FDP and the workshops also. So I would like to thank you very much on behalf of Department of IT and Tripura University also. Thank you, sir.
Thank you. Thank you. So with due permission, now I am leaving.
Okay. Have a good day, sir.